What is the specific problem addressed in the paper related to training instability in machine learning models?
The specific problem addressed in the paper related to training instability in machine learning models is the numeric deviation that can lead to loss spikes during training. The paper focuses on understanding how numeric deviation between an optimization technique, such as flash attention, and its baseline can accumulate errors over the course of training, potentially causing interruptions in the training process. The research aims to quantify this numeric deviation and its impact on model weights, ultimately investigating whether it contributes to training instability. By developing a principled quantitative approach to analyze numeric deviation and its downstream effects, the paper seeks to provide insights into the potential causes of training instability in large and complex machine learning models.
How does the proposed method work in quantifying numeric deviation in training optimizations? Provide a step-by-step explanation.
The proposed method for quantifying numeric deviation in training optimizations works through a two-phase approach. Firstly, a microbenchmark is developed to perturb numeric precision in the given optimization. This involves numerically implementing the optimization to analyze different numerical precisions and apply potential optimizations not easily achievable with the original CUDA implementation. The microbenchmark allows for varying precision inputs and modifications inside the algorithm, which is crucial for studying numeric deviation. Secondly, the method evaluates how numeric deviation translates to changes in model weights through a data-driven analysis based on the Wasserstein distance metric. This metric is used to measure the similarity between tensors and incorporates information about the shape of the tensor distributions to quantify weight differences accurately. By utilizing these two phases, the method is able to provide an upper bound on the amount of numeric deviation for a given optimization. It helps contextualize the impact of training optimizations on numeric deviation by comparing the observed deviation to a baseline and understanding how it affects downstream model properties. Ultimately, this approach allows for a principled analysis of numeric deviation in training optimizations and helps in identifying potential instabilities that may arise during the training process.
What are the theoretical or practical benefits of using the flash attention optimization technique?
The theoretical and practical benefits of using the flash attention optimization technique include accelerating the attention bottleneck in transformer models, reducing memory overhead, and improving resource utilization. Flash attention aims to minimize the memory requirements of the large similarity matrix used in the attention mechanism by using techniques like tiling and recomputation. This optimization allows for the calculation of the matrix one tile at a time, eliminating the need to materialize the entire large matrix. By incorporating rescaling factors to ensure consistent calculations without global information, flash attention achieves a 14% speedup in the forward plus backward pass for models. Additionally, flash attention offers increased efficiency and resource utilization, making it a valuable technique for speeding up model training processes. The technique addresses the system performance bottleneck of the attention operation in transformer models, which is crucial for modeling sequence-to-sequence tasks effectively. Ultimately, flash attention provides a way to improve the speed and efficiency of training large models, making it a valuable optimization technique in the field of machine learning.
How are the model weights compared between models trained with flash attention and baseline attention?
The model weights between models trained with flash attention and baseline attention were compared using two metrics, max_difference and Wasserstein distance. The max_difference metric calculates the absolute difference between weight matrices and takes the maximum value, providing an upper bound on the deviation. On the other hand, the Wasserstein distance metric measures the similarity between tensors by considering the shape of the distributions, with lower values indicating higher similarity. These two metrics were used to quantify how model weights change throughout training when flash attention is implemented compared to baseline attention. The results showed that models trained with flash attention exhibited changes in model weights during training, as indicated by both the Wasserstein distance and max_difference metrics. The comparison of weight differences over the course of training under different scenarios, including different random weight initializations and different numerical precisions, helped to contextualize the significance of the weight changes introduced by flash attention. Ultimately, the study found that flash attention introduced roughly 2 to 5 times less model weight deviation compared to low precision training, as measured by these metrics.
What were the results in terms of model weight deviation when using flash attention compared to low precision training?
The results showed that using flash attention introduced roughly 2 to 5 times less model weight deviation compared to low precision training. The study quantified the impact of numeric deviation caused by flash attention by analyzing different numerical precisions and their effects on model weights. The analysis found that flash attention exhibited roughly an order of magnitude more numeric deviation compared to baseline attention at low numerical precision, BF16. By utilizing metrics such as the maximum difference and Wasserstein distance, the study was able to quantify and contextualize the observed numeric deviation. The research demonstrated that while flash attention may cause numeric deviation in the attention output during a forward pass, the impact on model weights during training was relatively lower compared to low precision training. The study further compared the rate of change of weight deviation for models using flash attention to different model initializations and different precisions, FP16 versus FP32, showing that the weight deviation with flash attention was bounded by random model initialization and low precision training, introducing roughly 2 to 5 times less model weight deviation as compared to low precision training.
What future research avenues are suggested in the paper to further investigate training instability and numeric deviation in machine learning optimizations?
Future research avenues suggested in the paper to further investigate training instability and numeric deviation in machine learning optimizations include 1. Investigating the impact of various other optimizations on numeric deviation. The paper suggests widening the scope of analysis beyond flash attention to explore how different optimizations, such as the Winograd algorithm, kernel fusion techniques, and other attention optimizations, contribute to numeric deviation and potential training instability. 2. Developing proxies to understand training instability. The paper highlights the importance of developing proxies to better comprehend training instability, such as examining the exact point in training where loss spikes occur and correlating this with measured weight deviation. This approach could provide insights into the relationship between numeric deviation and training interruptions. 3. Exploring the relationship between training instability and hardware reliability. Future research should delve into how hardware failures and system reliability impact training interruptions and instability. Understanding how hardware failures contribute to stopping training jobs, and the implications for system overhead could provide valuable insights into improving training reliability. 4. Quantifying system overhead due to training interruptions. There is a need to quantify the additional system overhead associated with queuing and requeuing training jobs after loss spikes occur. Understanding the impact of these interruptions on system efficiency and resource utilization is crucial, especially when training at scale. 5. Investigating sustainability implications of training instability. The paper suggests exploring the sustainability implications of frequent training interruptions, such as power surges and fluctuations in data center power consumption. Research in this area could inform the design of low-carbon, power-efficient infrastructure for data centers to mitigate the environmental impact of training instability. In conclusion, the paper proposes several avenues for future research to deepen our understanding of training instability and numeric deviation in machine learning optimizations, emphasizing the importance of exploring a broader range of optimizations, developing proxies for instability analysis, investigating hardware reliability, quantifying system overhead, and addressing sustainability concerns.